So we've now introduced the concept of chemical equilibrium, the idea that reactions not only happen in one direction, but they forward direction, but they often happen in the reverse direction as well. We're going to move beyond this qualitative understanding and start to get a little more advanced and a little more quantitative by talking about something called the equilibrium constant. The equilibrium constant, okay? The equilibrium constant comes from an equilibrium expression. So let's say we have a reaction where it's, AA plus BB, and we're in equilibrium, so we know we have the double arrow, okay, forming CC plus DD. We know that since this is at equilibrium, the forward reaction is happening at a certain rate, okay, rate RF, and the reverse reaction is happening at a certain rate, okay, rate reverse. What we can do is we can write a little expression that relates the amounts of each compound to each other, because that's what's unique about equilibrium. It's a set of conditions where the forward and reverse reaction rates are equal and the concentrations are staying constant of each compound. So how do we write an equilibrium expression? So just to be clear, this is the equilibrium expression. So it's kind of like in a rate law when we said it was an equation. The equilibrium expression is an equation. And the way we write it is the equilibrium expression is K, a capital K, not a lowercase. So lowercase k is for rate law. K sub C, that has nothing to do with the C here. It doesn't have anything to do with that. It's just for the equilibrium constant in terms of concentration, is equal to, okay, the concentration of the products divided by the concentration of the reactants. So we're going to take our products and put them on top. So it's going to be the concentration of C to the power of C, which is the exponent, times the concentration of D to the power of D, which is the coefficient and also the exponent, divided by our reactants. So the concentration of A to the power of A from our coefficient times the concentration of B to the power of B, our other coefficient. So this right here would be the equilibrium expression for this equation. And then we'll do a lot of problems where we calculate certain concentrations and equilibrium constants and whatnot using it. What we're going to do in a minute is practice writing these expressions from chemical reactions like this. But first I want to think about, what does this actually mean? What does the idea of equilibrium actually mean? So let's say we have a reaction, to simplify it, A to B, okay? And we start with, here's our amount of B, and here's our amount of A. So once the reaction starts, A starts turning into B, so the amount of A is decreasing, and the amount of B is increasing. Eventually, we're going to reach a point where B starts turning back into A. And this is going to happen until these rates equal each other, until the forward rate and the reverse rate equal each other. At that point, when are we at equilibrium? We've reached equilibrium according to this spot. And how do I know that based on the graph? Let's say, this word right here wasn't labeled equilibrium. How do I know? Well, since I have concentration on the y-axis, I can see here the concentration of, in this case, B, is remaining constant. It's not changing. In addition, the concentration of A is remaining constant. It's a flat line. It's not changing also. That doesn't mean that the reaction has stopped. The reaction is still going. It's just that A is turning into B and B is turning into A at the same rate. So the amount of each is remaining constant. Okay? So these are the type of graphs that we'll see. You might have to be able to identify when is equilibrium occurring based on these graphs. You would want to look at when the concentrations start remaining constant. In terms of writing these expressions, okay, what we could do is, if we know the concentration of A and the concentration of B, we could determine what K is. Because for this reaction, K would be equal to the concentration of the products, B, to the power of 1, because there's no coefficient, divided by the concentration of A to the power of 1. So now what's cool about this is if we know this concentration here of B and we know this concentration of A, we could plug those in and we could figure out what K is. When you're writing equilibrium expressions like this and like this, there's two key things you need to keep in mind, okay? Number one, solids don't appear in expression. So if you had a reaction where it was like Na solid, blah, 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 this compound does not show up in the equilibrium expression. It's the same thing for liquids. Liquids don't appear in the expression as well. Neither of them show up. Only aqueous, AQ, and gases show up in the equilibrium expression. So let's get some more practice. Let's say you had this question. Determine the equilibrium expression. I've underlined this because you need to know in your mind what does that mean. That means K equals something. Okay? For the reaction below. Well, what is that K equals something? It's products divided by reactants. So my products, NH3. So it's NH3, the concentration of NH3, to the power of 2, divided by my reactants. In this case, the concentration of H2 to the power of 3 times the concentration of N2 to the power of 1. There would be my equilibrium expression for this reaction. Pause the video and go ahead and try this one by yourself. So for this reaction, the final answer would be K equals O2 to the power of 3 divided by O3 to the power of 2. A small thing to note, we can use pressure as well as concentration. So if these were given to us in pressures, like ATM for example, the values, we could also write that this is equal to the partial pressure of O2 to the power of 3 divided by the partial pressure of O3 to the power of 2. So you need to be familiar with writing it either way, depending on if it's concentration or if it's pressure data that's given. Depends on the problem. How do we do quantitative problems with this? So, same idea. Consider the reaction below. If the concentrations of N2O4 and NO2 are 0.0014 molar and 0.0172 molar respectively, what does that mean? It means the order that these show up, the order that the numbers show up afterwards, correspond to that compound. So this concentration is for this compound, and the second concentration, do that in a different color, is for the second compound. What is the equilibrium constant? Ooh, so now it's asking for what is C actually equal to as a number. So I need to write the expression first. The expression would be K equals concentration of NO2 squared divided by the concentration of N2O4. But now that's just the expression. We're trying to figure out the equilibrium constant. So now we got to plug in our numbers. The concentration of NO2 was 0.0172 squared divided by concentration of N2O4, 0.0014. And if we solve that, what we would get for a value is about 0.211. The equilibrium constant is special in the fact that K will have units depending on the equilibrium expression. So in this case, you need to plug in the values similar to how we did for the rate constant. So NO2, the concentration was molarity, so it'd be molarity squared over N2O4, which is just molarity. Boom, boom. So the units would just be molarity for this equilibrium constant. However, very rare that you actually care about the units for K. All we need to know how to do right now, don't stress about the units, we need to be able to write the expressions if you're given an equation, and then solve for either k, or I could have given you k and asked you to solve for one of these values instead. The last thing we need to know is, what does k actually tell us? What does this number actually mean? Well, to think about that, we need to remember that we're talking about reversible reactions at equilibrium, where we have two reactions going on. A is turning into B, and B is turning into A. The amount of this and this does not have to be equal. You might have more of one than the other. K tells us that. Because remember, K is equal to the ratio, essentially, of the products divided by the reactants. Okay? Not exactly, because remember, it depends on the coefficients and everything as well. But this is essentially what it is. So let's say we're at equilibrium, and we have 10 molar B and 2 molar A. If we plug that in, we would essentially get 10 divided by 2, which is 5. Let's say we reversed it, where now you had 10 molar A and 2 molar B. Again, a different reaction, for example. Then K would be equal to 2 over 10, which is equal to 0.2. This is going to be very interesting for us because, as you can tell here, this value is bigger than 1, and this value is less than 1. Whenever K is greater than 1, that means the reaction favors the products. Which means that at equilibrium, write this down, at equilibrium, the concentration of products will be greater than the concentration of reactants. And you can remember that by thinking that it's always products over reactants. So in order for this number to be bigger than 1, the products, the numerator, has to be greater than this number, as in this example. However, if K is less than 1, then the reaction favors the reactants. Which means there will be, again, write this down, more reactants at equilibrium than products. As we can see here, since there's more reactants, the denominator is bigger, so when we divide by a bigger number, we get a number that's less than 1. And of course, if they were equal to each other, then K would be equal to 1, and the reaction doesn't favor either side. It's in the middle. So we want to know, if I gave you a value of K, you would have to be able to tell me, does it favor the products or the reactants, and why? Graphically, what would this look like? Here are two examples. Here's where K is greater than 1. So first thing, how do we tell we're at equilibrium? Well, about right, it looks like about right here, we would be at equilibrium because the concentration of reactants and products is not changing. As we can see, concentration is on the y-axis, and we have more products than reactants. So therefore, K is greater than 1. On this side, we're at equilibrium about here. I can tell because the concentration of products and reactants is remaining constant. Now we can see that I have way more reactants than products, and therefore K is going to be much less than 1. So what you need to be able to walk away with today is an understanding of what K tells us, depending on if it's greater than 1, less than 1, or equal to 1, and why. You need to be able to write equilibrium expressions like this from an equation, as well as solve for K, given values, and write more expressions for any equation that's given, knowing that solids and liquids don't appear in the expression.